Hello, good afternoon. My name is Branka Dimitrijević. I would like to welcome you here at the seminar at Glasgow Caledonian University and also at our online webinar. Our project, CIC Start Online, disseminates outcomes of feasibility studies and academic consultancies that are undertaken by 7 Scottish universities in collaboration with small to medium-sized enterprises operating in construction sector. The project is funded by European Regional Development Fund and Scottish Government. Before I introduce our speaker today, just to say if there is a fire alarm today, we will have to stop the seminar, but we will resume later, so you can rejoin us later. In any case, we will also publish video recording of this event on our website, so you can watch it anytime later. We plan to complete a presentation, to finish presentation around 1:30, and then there will be 30 minutes for questions and answers. Our online audience can use chat facility to ask questions. You can start asking questions at any time during the presentation. If your questions are not answered by 2 o'clock, when we will finish, you can also send them, well, they can be answered by email. They will be answered by email later by our speaker. Today's seminar title is Solar Wall Systems for Domestic Heating, an Affordable Solution for Fuel Poverty. This is the feasibility study that was undertaken by Heriot University in collaboration with Changeworks. And today we have the speaker, Dr. Wang of Heriot University, but also in this feasibility studies, Professor Prof of Heriot University and Nicholas Heath of Changeworks were involved, but they were not able to attend today. So I would like now to invite Dr. Wang to start with his presentation.
Okay, good afternoon. Thank you very much for giving me this opportunity, and also thank you for audience, particularly those logged on to online to see this. And it's particularly nice to see some colleagues, Dr. Fiona McNallen. Actually, this presentation was made by 3 people, Professor Prof and Nicholas Heath and myself, and they are unable to come, so therefore I will present their parts on their behalf. First of all, I would like to have an overview what we're going to cover today, and basically we were going to have an introduction, and the content is prepared by Professor Prof. And then we'll talk about the opportunities and challenges and for this project. And then that will followed by the principle of the system. We'll talk about some theoretical background for that system. And then we will talk about the methodology we used for this study. And we'll present some results, what we have got so far. And later, we will go over what we are doing currently. And finally, we will have the questions and answers. And the introduction, Professor Prof is really keen to present some of our latest research in our own group in Heriot University. So basically, we will try to confine all those information in a short period of time and also cover those most relevant areas to this project. So the research carried out in architecture engineering covers a big range. Now, what I'm going to cover actually are those major ones related to sustainable development in built environment. The first one actually is a big one, and Sue somehow is the key person is to build an eco-village near Heriot University on campus. So what you can see, this is Heriot University, and that part, so this is the university, and then that part is currently a research park. We're going to build the eco-village around this area. And that eco-village is not just to promote some sustainable living style, but also we want to use this site as a testing platform in which we will try to use as much as possible this renewable and sustainable technology. For example, here we can see wind turbines, photovoltaics, solar thermal. And we also want to examine the built forms. For example, here we can see this traditional timber frame structure and this panel structure. One of the particular area we are interested is to see the thermal mass, how thermal mass can be utilized to, improve the indoor thermal environment and minimize the energy for heating in winter and prevent overheating in summer. Then we also have a big research area into sustainable community design. This is a newly developed course in our university, in our school. It's to promote sustainable community life and design. Through also that research in looking into the thermal performance of tenement buildings, which characterized by heavy thermal mass and a thick uninsulated solid stone wall, and that was a project carried out in 2008. This actually was one of the inspiration for my own project. In Heriot, we also use large amount of modeling facility to foresee what kind of real situation will be, and particularly in design stage. So therefore, we can test number of design options and see how they affect environment and affect the energy consumption. And in Heriot, we have some wide range of laboratory facilities. This is a wind tunnel, and we used this one to see how we can use shuttle belts to create a better outdoor space. And that was the real site we investigated. You can see how wind can be shadowed by these wind shuttle belts. And that is a helidome, which we used to test solar control for particularly for buildings in hot countries. And apart from this small device, we also have computer packages allow us to simulate the solar effects or shading effects and the thermodynamic thermal performance. Buildings on contaminated land actually present some problems like radon and the volatile organic compound entering into the building. So therefore, that is also part of research. We look at how we can minimize the soil gas entry to domestic buildings through the substructures. Pollution around the built environment, again, is another big area in our research group. And part of the wind tunnel, we have this computational fluid dynamics allow us to simulate wind distribution, wind environment, and the pollution concentration in a large built-up area. And again, using the computational fluid dynamics, we can study indoor air quality, and particularly this becomes a very powerful tool for building service engineers to optimize their design to remain good air quality but minimize the energy consumption. Wind tower design, again, is another feature for low carbon design, low carbon buildings. And this one actually is highly relevant to what we are going to talk about. This is to assess low carbon technology, not only look at the technical benefits, but also look at the financial ones to foresee the payback area when we consider life cycle model. And in Heriot University, we also look at other non-technical areas. For example, that is the energy consumption analysis to look at occupant behavior. And because we have a large amount of students coming from different countries, so therefore that provides us access to wide range of countries, and then we can look at their living style affect the energy consumption. So these are some highlight results. So I'm not going to go over these details. Part of the energy, we also look at acoustics, for example, the noise. And in the urban design, we try to create all sorts of interesting soundscape, so therefore can improve the urban environment. And again, we have a very good facility in our school and to facilitate all sorts of research. Here are some other studies for access for urban facilities. And this is another study looking at behavior of occupants in low carbon building design. So we actually try to investigate the three groups of interest: people, occupants basically, and the environment and climate basically, and the buildings. And as I mentioned earlier, we have a large number of students coming from other countries. So therefore, we felt that the thermal comfort has to be considered under the cultural background, particularly adaptability. So therefore, we have this study carried out in a number of different countries. Wind turbine studies. We had a small program to look at wind turbine design. So the wind tunnel facility and computational fluid dynamics were used as modeling tools. So therefore, we can optimize the blades and nacelle and to work out a best configuration for these wind turbines. As I said earlier, Prof, actually, she is the promoter of this lot of renewable low carbon and research. And one of her contribution actually was organized this carbon counting conference, one in London, the other in Edinburgh. Basically, we consider any real low carbon practice has to be a collaboration between technology people, researchers, and the practitioners, and also government. And so therefore, that is the her plan and her vision. And because of her inspiration, I started this research looking at how we can utilize solar in some traditional Scottish buildings. Now, first of all, I would like to talk about some challenges and opportunities. And most of the contents here were prepared by my partner, Heath, in Changeworks. Now, In Scotland, we have about 25% of homes are tenement. And the figure in Edinburgh is even higher. We have about 45 the house form or tenement. And about half of those actually were built before 1919. Those buildings are built for communal living. Ideally, this building actually can be very efficient for energy because every household has less external surfaces for heat to lost. But unfortunately, those buildings were built many years ago. So most of those external elements are not insulated. And again, big glazed windows, open flue for air to move around, and old heating systems, very inefficient. So therefore, putting all this together, very often these buildings are energy inefficient. Another difficulty for this actually to improve the energy efficiency for these buildings, we found many available technologies are very expensive. And even some buildings are listed, so therefore you can't do anything, for example, change it to double glazed windows or make any internal or external insulation. And the other issue is that although some governmental funding are provided for energy efficiency, but they are more or less for cavity wall insulation and a loft insulation. And for these tenement buildings, those technologies are not covered by those grants. In addition, many of those tenements are in low income category, so therefore those technologies are not affordable for them. Apart from those difficulties, we have some other due to the nature of this tenement. It's basically the communal nature of those buildings, so therefore any plan has to be agreed by all the parties in a particular building. So therefore that increases the difficulty. Then why to improve the energy efficiency is important, and all my research is justifiable. We have to think about in these 4 areas. First of all, fuel poverty in Scotland, and then the promotion of health and the well-being, and then foreseeing the costs of energy bills. And finally, we look at the solar availability in Scotland. According to this survey carried out in 2005 by Changeworks together with Edinburgh Council, we actually found there's a high percentage of fuel poverty in Edinburgh area. So therefore, if we look at the map, those red indicates the problems of fuel poverty, and more or less they are very, located in the central area of Edinburgh, and many of those actually are in old buildings. If we look at the causes for fuel poverty, there are these 4 major reasons. One is low income for those households, so therefore the money paid for heating and other fuels in domestic household can be over, more than 10%. So the income is one, and the other is increase in fuel prices. And the third one actually is the major one, which contributes to the high fuel poverty in Edinburgh central area is the poor energy efficiency for those buildings, which we are trying to tackle. And then the final one is under occupancy, and that can be dealt with by city council through better management of this tenements. In Scotland, we tried to eradicate this fuel poverty by 2016. So consider the time scale, actually our research becomes important. Health and the well-being for our tenements actually is another thing we have to consider to improve the thermal performance of buildings and the heating quality. So therefore, we can improve our living, and that is, the strength of modern living. Now, the significant evidence is the increase of bills, because people want to live more comfortably. So therefore, they want heat longer and to higher temperature. And on the other hand, the price of energy actually is increasing. This is a survey. Look at average household in Scotland. The fuel bill increases stably, particularly after the new millennium. We have a steep increase on the household bills. And then if we predict what is going to be for the prices, and it's even more miserable. We have, there's a steady increase in electricity bills, and there's an even jump for the electricity bills in 2020 and between 2020 and 2024. So therefore, it's urgent to think about any efficiency for heating and some other methods. Weather is becoming more unpredictable because of global change. Obviously, summer becomes warmer, and winter is becoming wetter. And the forecast says that if the temperature increases slightly, the snow and ice melt can make Scotland cooler in winter. So, putting all these things together, we feel that we have to deal with this tenement buildings, although they are difficult to handle, but we have to try our best. This was the project started by Changeworks. They installed some solar heating systems in Roriton Place in Edinburgh. Basically, they have solar panels installed on some of the roofs. You can see actually those panels are between the two external slope of roofs. So therefore, from outside, they are not visible. So that is the way to pass the planning permission. And the areas are big enough to provide hot water. So therefore, they provide this hot water for the houses under the flats underneath this piece of roof. And these are some pictures showing the panels are installed. And so therefore you can see the background of the after seat. So really they are very well hid by the roofs, so you can't see from outside. Changeworks also produce large amount of research guides for other tenements or housing organizations to improve the energy efficiency of their buildings. So these are some examples, their research output. Their website actually is very well organized. There are lots of useful information. And here, just one example, provide information for tenements to improve their own flats to make them more energy efficient. So these are the documents you can download from their website. And some example here is how can you improve your heating by replacing electric heaters to some more efficient devices. Really, next step, Changeworks decided is that we have to explore more other opportunities to implement the research available currently. Now, let's look at the opportunities for this to use solar in tenement buildings. Here we carried out a modeling study using real weather data. You can see that this blue line represents the heating for domestic flats, and this baseline is domestic hot water. So this green line represents how much solar available if we have a small area available for tenement flats shared by different floors. So we can see here, during the winter, obviously what we all expected, low solar, so therefore not enough solar energy can be used. But after middle of February and before middle of October, so we have actually more solar available than can be used for domestic hot water. Now, what I didn't mention for this Lorested Place project actually was that the solar heating, solar collection is only for domestic hot water. Most solar projects actually is to use solar to heat water, to provide domestic hot water. But from this analysis, we see actually domestic hot water has only small part of the energy demand. A large amount of energy actually is used for heating. And this slide really shows actually there's a big opportunity. You can see from here, we have more solar available for domestic hot water, and this can be used for heating. If we look at bungalow type, so therefore roof area doesn't have to be shared by different floors, we have more energy can be used. So therefore, that actually really gives us an opportunity to use the solar. And now let's look at the principle of this solar wall system. Now what we see is a conventional solar hot water system. We have a solar collector and a cylinder to store heat. And when this heat, the water can be heated again by a gas boiler when there isn't enough solar available. So basically, the gas boiler can provide backup. Now, problem for this is that when solar is strong, and then you have to extract heat constantly to maintain good efficiency for the solar panel. But when the water is already hot, so therefore the efficiency of panel collection drops. And that happens all the time for domestic buildings, because domestic buildings actually use hot water mostly after they come back from work. So this is afternoon. So this is another challenge. So it's a shift between solar availability and heat demand. Now, to improve this, we basically try to extract heat as much as possible from the solar panel and use extra solar storage. We have seen some solar heating system with 2 cylinders. Now, so therefore, we basically replace one of the cylinders by the wall. We use solid stone wall to store the heat. And we know that although the specific heat of stone is probably just 1/4 of the water, but the density can be 4 times higher than water. So therefore, putting them together, actually the same volume of stone wall can save as much as the same volume of water, the heat. So therefore, that is the principle we're going to, this project is based on. Now, let's look at the methodology that was used in this research, this feasibility research. Basically, the objective of the feasibility research is to see how much energy can be stored by the solid wall and how we can maximize the heat store, and so therefore the heat collection from the panel can be maximized. To do this, we need to first of all design a parametric study in which we try to identify the key variables, so then see how these variables can affect solar collection and affect heat storage in the solid wall. And to carry out this parametric study, we use 2 models. One is using computational fluid dynamics. The other is to use a real mock-up in laboratory. And finally, we also want to see the financial costs and how long it takes to have the payback. Right, parametricity, as I said earlier, this is a very common method used in many research studies. It allows a number of key variables to be examined closely to find out quantitative relationship between those variables and these test variables, which are the solar collection at the panel and the heat storage in the solid walls. So therefore, we try to look at the main key input temperatures of the water coming and return to the panel, and what temperature goes into the solid wall and after. And then to look at the water flow rate to the panel and to the cylinder and to the wall. So therefore, these are the key variables. And the heat exchanger basically allows to calculate the temperature difference and the heat flow, water flow rates. So therefore, they can be calibrated together with the main output is the solar heat collection at the panel and the storage in the solid wall. Developing the computational fluid dynamics model is the key in this feasibility study. And the major feature of that model actually is it's dynamic. We can run it 24-hour cycle to look at the change of solar input and then to see how the wall responds to the change of solar input. And then the other feature is that because the nature of CFD, it allows us to calculate pretty accurate the heat exchange between the water flow to the pipes, so therefore to the solid wall, and then from the solid wall to the air on the 2 sides. So therefore, that actually is the biggest the advantage of this research, and I will show you this later. How we develop a model to give us dynamic simulation and also the high resolution of this from in the wall is we use this internal solid wall. We have this solar panel attached to the wall. The heat exchanger attached to the wall, and we have somewhere on the roof the solar panel. So the hot water pumped into this panel, and the panel, because in good contact with solid wall, so the wall is heated up. Now we assume the hot water goes in this parallel pipes, vertical pipes, at the same temperature. So therefore, we can just simulate one slice. So we cut through this slice. So therefore, we can simulate the dynamic feature without lose the actually resolution of the geometry of this wall. Now, if we take this slice, magnify it, this is a pipe, half a pipe. We simulate the symmetric nature of that slice, so therefore that further reduces the computational cost. And then, so therefore, the pipe inside is in contact with the solid wall, and the other side in contact with the plaster. So therefore, the heat exchange between these two can be calculated accurately. On top of this, we also calculate heat exchange between the surface of this plaster with room air on this side, which represent living room, which is used during the daytime. The other side is bedroom, which is used during the nighttime. And then, so the heat change between the solid wall, external surface, and the air can be calculated. So we can see that when hot water goes in, now it heats up immediately this plaster, and then heat the room, which is used in the daytime. This is the time when you have maximum solar input. Now, it takes much more time for the solid wall to heat it up. And then it takes even longer to heat the room. And the room actually is used during nighttime. So because of this delay, we can actually very efficiently use the heat. Heat the daytime use space during the day, and then heat the nighttime use space during the night. So that actually is another feature of this system. Now, next slide actually is that I'm going to show you one particular horizontal slice of this computational domain. So here we have this stone wall here, and we have a slice of plaster, and that representing a cross-section of the pipe running inside as hot water. So therefore, for the computation of fluid dynamics, we calculate heat change, which is primarily convection between the fluid of water and the solid plaster and the wall. And then we also calculate convection and radiation exchange between the surfaces of the plaster and then the air, and the same on this side. So therefore, by doing this, we can simulate the real phenomenon of heat exchange in this system accurately. Right, now, safety model normally need validation, because nowadays all those commercial safety packages are designed in a way, no matter what you input, you can always get some results, and the results are always colorful. So therefore, they can be very deceitful. So therefore, to gain confidence of our model, we need to collect some measure data to validate our model. So therefore, the model can be later on used as a parametric study. We can play with. We can change, all input and then see output and find out what the relationship between the outputs and the inputs. Now, this is the schematic diagram of this real system in laboratory. First of all, we look at this big panel. This is a plastic panel. It's called aquathermal, provided by one of our sponsors. And so they are attached to the wall and then leveled by a plaster. So the other side is a solid wall. The front is plaster. Now, there's a valve and a meter. So therefore, we can monitor how much heat input through the meter. Now, the hot water actually is from the laboratory hot water supply. Now, we manipulate the temperature by mixing the hot water from hot tap and the cold water from cold tap in a different rate. So therefore, we can tune the flow rate, tune the temperature to simulate the available of solar collected at the solar panel. And then we put it onto the wall. This is a diagram from the literature booklets, how we can install the solar, the heating panel to a solid wall. And there are a number of different ways, but for us, we basically want to use this wall to store heat. So therefore, we use a plaster to cover it up completely. So other measures can be you just use a board to cover it up. And so there are a number of ways to do this. And so if you look at details, this is the panel before being put into the wall. And this is the illustration showing how the panel is attached to a brick wall. In our case, it's a solid stone wall. And then this is the picture showing the arrangement in our laboratory. In our laboratory, this is a climate chamber in which we can control the temperature in a pretty, accurate level. And so we have a solid wall and a PC allow us to monitor all those key variables. And then this is the cross-section showing how those temperature sensors, this is a cross-section horizontally. So this black one shows the panel. Therefore, we measure the surface temperature at the plus side and then inside the panel, and then interface between the plaster and the solid stone wall, and the one in the middle of the stone wall, and finally the other side of the stone wall. We have two places, so therefore this allows us to monitor the temperature distribution through this wall structure. Now, the third model we used, in addition to the computational fluid dynamics model, laboratory model, this is a cost model. Here we consider initial costs, and then maintenance costs, and then operation costs, and then replacement costs. Put them together, we have worked out the saving is S, and it's a function of how much energy saved, and the price and the increment throughout a year. So therefore, this is a very standard whole life cost model we used. So therefore, it helps us to work out the payback period of time. Right, now let's see some results. First of all, we use the measured data to validate our CFD model to see how good the model is. These two plots basically showing, the first one, we can see this representing where the pipe is. The hot water comes in, the red means the 34 degree roughly, and then gradually this part being heated. And then the air next to the plaster actually being warmed up, so therefore the convection raises the air. You can see the arrows show the direction of the air movement. And similarly on the other side, which is bedroom air, and this part is a solid stone, so you can see this is the second day heating started. So therefore, previously the other day heated, so therefore the temperature somehow is warmed up, and that warms up much quicker. So therefore, the temperature is already 25, 26. But this part is just start, so therefore about 20 or something. All right. Now this actually is the end of 48 cycle. The wall, the solid stone wall, is in a pretty warm condition. Right, then that slide shows the comparison of measured data in terms of temperature with the predicted one. The solid lines, these are the predicted ones. The blue one is plaster, and red one is the solid wall, and the cross one is the measured data. That is a heat input from tap water, the hot tap water, representing the solar collector. So we can see actually they agree to each other pretty well. And this doesn't just provide the validation, but also give us an insight to see the performance of this system. For example, because we use the real data, so therefore in March, very often we found early morning we don't have much sun, so therefore the input is less. But afternoon, it becomes stronger. So therefore, we have an increase after, for example, 1 o'clock in the afternoon, and then sun sets. So therefore, there's no input at all. And we see this in response very quickly in the plaster increase. But for the wall, it increases very, very slowly. And when there's no input, and then the plaster drops, but the wall still increases. So this is what we call thermal mass, and that is what we want to use. Okay? As I mentioned earlier, Professor Surov, she proposed the eco-village, and inside which we have some buildings designed deliberately with heavy thermal mass to utilize this heat storage. Now, next slide actually allow us to analyze how much energy is pumped into the system and how much is being stored in the wall. This is again the heat input, and so it increases in the daytime and to the maximum during the afternoon, and then stops, and then starts the next day, increase again. So this is the midnight time. Now, if we look at this, the heat delivered into the living room, basically it's through the plaster side to the living room, and increase during the daytime, which is good because the living room is to be used in the daytime, so therefore they need to be heated. The green one is the heat lost from the solid wall to the bedroom. So it basically is a zero because it's heated up. So there's nothing to contribute to the heating to the bedroom. So therefore, there's nothing going into the bedroom, which is what we want. And then to the afternoon, it gradually is warmer than air. So therefore, there is some heating into the bedroom. And in the living room, it starts to drop. Okay? Now, if we consider the heat stored in the solid wall, you can see this is a black thick line. So during the daytime, large amount of heat being installed. And when there's no heat input, the heat installed in the solid wall start to release into the two sides. Okay? Primarily to this the bedroom, and partially to the living room. And particularly, if we look at this one, after 9 o'clock, there's nothing to living room because there's no one, less chance is less likely used, but more released into these bedrooms. Okay, and then that heat input maintained rather stable throughout the nighttime, and then started again next day. Okay, so this actually allows us to work out a best control algorithm later on for the control panel for the system, and that is one of the key area we're going to investigate later. Now, this slide shows the cost model, where we have this is an initial installation, and this is the replacement, and we have some kind of maintenance, very small amount of maintenance, and that is really drop in terms of energy saving, because that some amount of energy collected from solar you don't have to pay, and this offset the energy you buy from either gas or something. So therefore, this is a negative. So add them together, you have this one. So this is a payback. Currently, we see probably about 16 years of payback. This sounds pretty long, but anyhow, that is the prediction. Finally, I would like to go over what we're going to do now. The first one, as I just mentioned, to work out the algorithm of control. That is one of the work we are doing. So basically, control is to make sure that the system is very well integrated together and then work in an optimized way. The other thing is actually work to see the balance between the demand from domestic hot water, which is coming from cylinder, and the other is for heating. Basically, now we have two stores. One is hot water, the other is a solid wall. So how we arrange this, heat store is the major target at the moment. Now, apart from this, there are many, many practical problems. So far, more or less, we rely on theoretical work. And for example, in CFD modeling, we don't have to consider anything like how long it takes to install and how much disruption to the household. And these are very practical problems we have to consider, but these are not considered at the moment. And even in laboratory, all conditions are in a very well-controlled manner. So therefore, we haven't encountered any real problems that will be very likely to happen in reality. Right, so basically, we have this device. Previously, we didn't have this cylinder. We took the hot water from taps, right, to simulate heat input from solar panel. Now we try to integrate together with two storages. One is the cylinder, the other is solid wall. And so therefore, we have this installed and one panel at our side, which is provided by one of a long-term collaborator, CIC. And so we have a panel. This is about 2.5 square meters. We worked it out. This is enough for 1/3 of flat, okay, one bedroom basically. And so therefore it provides enough for 1/3 of domestic hot water requirement and heating. And so that was about what is going on now. Finally, I would like to say thanks to, first of all, CIC Start provide this opportunity, we can do this study. And also the IES provide our solar panel. And then this Ormandy Aquasome provide us the panel. And then Fletch is in university. They give us some studentship for our master students who did this job for me. And that's it, basically. Thank you very much for your attention.
Thank you very much, Fan. Please take a seat there. Well, thank you very much for very interesting presentation. And now we have time for questions, both here from the audience in the seminar room and online. And we may start with a question by Tamer Gado online, who says, I would like to see more of the research and the comparison between the potential of using building thermal mass as opposite to water. So I will look out for the journal paper. Do you have any comments on this?
Yes, actually, I have submitted the paper reporting this project to a journal. I'm waiting for their comments. And in that journal, actually, I had some equations showing the comparison between the comparison between the solid wall and the water in terms of heat collection. But I have to admit that that calculation is based on a very simple assumption. We don't consider, for example, the convection in water, and there's no convection in solid wall. So in terms of this, probably water is more efficient in terms of store the heat. Okay. Have I answered the question?
Well, hopefully Tamer Gado happy with that question? Do we have any questions here in the audience? Yes, could we have a microphone over there? Please introduce yourself and ask the question.
Hello, I am
Yes.
George Loumakis. I'm a PhD student in Glasgow Caledonian University. In your cost analysis projection, you had, did you take into consideration the rise in fuel prices and electricity prices?
Yes, yes. We actually look at the, we assume there's a 7% increase in price. And so therefore, this was included. Yeah.
You had a slide previously that showed a rise in electricity prices, a projected rise, and we're having a huge spike in 2020, which lasted for like 2 years.
Yeah.
Could you explain why where the spike comes from?
Actually, I'm not very sure.
Yeah,
because
it wasn't part of your work. That's why I'm asking.
Yeah,
if, you know.
Actually, that jump wasn't included in the cost model.
Mm.
That slide was provided by Heath, and actually, I haven't got a chance to check it out. So I'm sorry,
Okay.
I can't answer this one.
Okay, no worries.
But if you leave me your email address, I will pass your email address to him.
Okay, thank you.
Okay. We have a question from Lijin Zhang. Is it possible to store the surplus heat in summer for winter use?
That is a very interesting question. Currently, we acknowledge there's a big shift throughout the year. For example, in winter, we need the heat most, but we don't have strong enough solar. And where in the summer, we have plenty of sun, but we don't need so much heating. And that is a problem. But currently, we actually just look at the daily shifts. For example, during winter day, we have more during the daytime, but we don't want to use so much. So therefore, the storage is primarily to shift the day pattern. There is a project in King's Langley. There's a Beaufort Court. Actually, they have a big heat store. It's by 22 meters by 22 meters square and about 6 or 7 meters deep. It's a water store, and hot water store during the summertime is kept there for about 3 months because there's a thick leak about 1 meter polystyrene to insulate the summer store. So therefore, the temperature in summer can be as high as 90 degrees or even higher in August, and then temperature still remain about 30 or something in November, where the heating is started. Okay, so there is a possibility to store heat, but it all depends on how much land available, because the project, the Beaufort Court, actually is in the near M25, so there's plenty land. For flat domestic buildings, probably we don't have such kind of luxury for space.
Any more questions here? We are still waiting for questions from online viewer. Here is one, again from Tamer Gaido, and he asks, well, a bit longer question. Using thermal mass as a mean of transporting heat and as a medium for storing heat is not new. What this research can provide are A, the integration with existing solar technology, and B, integration with existing buildings. However, I believe that the proposed idea is very promising for only new buildings, but cannot see the potential use with existing buildings, especially listed ones, which, as you indicated earlier in the presentation, are very difficult to change. Did you consider looking into prefabricated panels of thermal mass that can be installed into existing buildings?
Yeah, that is a very interesting question. Actually, the project started about 2 years ago when I was moving to a tenement building. And I saw the poor insulation, I saw the single glazed panels. I actually was very concerned about the bills we were going to pay. And so therefore, we had this in mind to tackle that existing tenement buildings, which is, I said earlier, is a hard to treat types of the properties. And so therefore, we had this in mind at the very beginning. Now, there is a manufacturer used this precast fabricated panels. So therefore, you can just screw it to the wall. So make an installation much easier. The other advantage of this system is you compare with the radiators, which takes a much considerable space in a room and make it difficult to furnish arrangement, something like this. So therefore, we consider a wall panel can give some freedom for interior design. So therefore, for either new building or old existing buildings, this is we consider this is opportunity, very good opportunity. Particularly, I have already been thinking about the old tenement buildings. We have a picture rail at the top, and then a pretty thick skirting board underneath. So in between, we have about 2 meters tall area to fix this panel. So that will be sufficient for our system. But anyhow, there are obviously many other practical issues we have to resolve to work out a detailed procedure, how to install it, and also the program for maintenance. Now, that needs a collaboration with some contractors who have been doing these heating systems over years. So therefore, their expertise can be very good input to this one.
Okay. Here is a question from Antoinette Charles. How feasible is this concept with social housing? This sector suffers from fuel poverty, and refurbishment activities are being carried out. Would the 16 years payback period be viable?
This is a difficult question. As I said earlier, so far the feasibility study has more or less concentrated on the technical feasibility, and this 16-year cost model is a simple, easy exercise to see how we can work it out. And really, we need more work together with Changeworks because they are more experienced in this kind of social aspects. How willingly those tenements accept this new technology and they were willing to collaborate more closely and sacrifice some of their own, for example, privacy during the installation, during the investigation and the maintenance, all sorts of things. And so therefore, it's difficult to answer this question at this stage, but we actually are looking into it.
A question from Gloria Law. Is there a projected installation cost for retrofitting the water circulating system in an internal wall, say in a tenement block as shown? The solid walls also would be structural, may have complications in installation.
Yes, that cost model was for both, for a cylinder and together with this wall panel. Okay, so actually it was predicted for a whole system.
Okay, do we have any questions here in the audience? If not, I have a few questions. Well, what if leakage happens in these installations? How would it be repaired? How likely would that be? Have you thought of these problems?
Yes, actually, we are aware of this, this problem, and we see this is the biggest problem whenever it happens during the installation or afterwards. But to be honest, I don't have the answer at the moment, and we're looking forward to collaboration with some contractors who have experience of installing any type of this kind of solar wall system. There's a wall heating systems, and I've seen some constructors who have this experience. And the manufacturer of the panel, the they should have many this kind of cases, and they should have experience for this. And we should work out later to consider this as a major problem in reality.
Okay. Well, while waiting for questions, I have some more. If there is not enough sunshine, for example, how easy it would be to switch back to backup from a boiler that is heated by gas?
Yeah, this is always a problem because most technologies of using renewables actually are not always stable. So therefore, either, for example, solar or photovoltaics or wind turbines, we need a backup for conventional supplies, for example, electricity from power station or gas from pipes. Now, in our case, we are thinking about, we have an extra coil inside the cylinder or connect together with the heating panels. So therefore, the solar provides background heating. If it's not enough, then the gas boiler steps in to provide extra. So this is again part of the future study in our research into the control algorithm.
Okay. Here is a question from the audience. Please introduce yourself and ask the question.
I'm Dr. Roberto Ramirez Iñiguez from the School of Engineering and Computing of Glasgow Caledonian University.
Okay.
What size of solar panel and wall panel did you consider for the capital cost recovery analysis for the prediction of how long it's going to take to recover the capital cost?
Oh, okay. Now, currently, we use 3 panels. It's about 1.5 meters wide and 1.5 meters tall. And that is just fun for one of the bedrooms. We consider a standard flat as 4 bedrooms. So therefore, there's 4 sides. And so what we saw, just 1/4 of the whole system. Okay. So basically, all the prices you multiply 4, we get the whole cost.
All right.
Yeah.
Thank you.
Okay. Here is a question also in the audience. Please introduce yourself and ask the question.
Hi, my name is Santosh and I'm a student of MSc Energy and Environment Management. I would like to ask, did you consider if they want higher temperatures? How would it be easy to achieve by the system?
Higher temperatures for cylinder or for panels?
No, for a room, if they
For room.
like maintaining the temperature.
Okay. Now we haven't considered that details yet, but we would imagine a normal thermostat in a room will be a part of our system as well. So therefore, if we want to change about 2 or 3 degrees, this can be done through the thermostat. But the panel, because currently the panel is made of plastic, so there's a restriction of how hot the water goes in. So therefore, to achieve a higher temperature can be done by increased panel in the initial installation, or to run it for longer time, or for more input from gas boiler. But anyhow, this can be done just using thermostat.
Okay. Here is a question also from Gloria Law. Was there any research into installation to stone walls that are structural and the complications that may arise?
Actually, we assume in the beginning those internal walls are also load supporting, because otherwise those walls would not be so thick. And the idea to use those walls for heat store actually is to find the solid, strong, and heavy. So therefore, there are structural walls for load bearing. No problem. Right. Okay. Good. Thank you very much.
There is another question from Tamer Gado. Did you look into applying the system in public buildings?
what do you mean by public building? Basically, what we actually
not housing.
Not housing. Now, currently, we have all this in mind is that it is a problem when you want to use the heat and there's no solar. For public buildings, probably the advantage of this system doesn't show, in full scale. For example, in an office building, and you want to use the hot water, and you want to use the heating, and it is during the daytime, so therefore you don't need a shift. So therefore, it will be better to use it for domestic buildings, which is used most during the nighttime when the solar is not available.
Okay. Another question: does any consideration need to be given to the type of plaster used?
And this is a very good question, but unfortunately, at the moment, we're having to think about it. Basically, from the manufacturer, they have made some recommendations. Basically, those plasters have to be stronger than ordinary ones because they are experiencing, the temperature variations. So therefore, they are stretching and contracting. So therefore, there is a requirement, and we can find out. I remember I read one particular section from the manufacturer. There is a requirement for the plaster.
Okay. A question from Malcolm McKillop. Would it be cost efficient to incorporate off-peak electrical energy into the system?
I haven't thought about this. I don't know. Off-peak. Yes, if we use the solar mass to shift demand, that can be useful, but depends on if the rate is cheaper during the nighttime. So probably we just use it, right? Rather than store it.
Question from Tamer Gado. Did you involve anyone from the practice to try to see how the idea could be applied in real projects?
Our partner, Heath, actually, he is looking after all these practical issues. And as I said earlier, currently we are at the moment considering more or less the technical aspects. So therefore, in the future, we will have more considerations on reality or to tackle with real problems.
Okay. Another question. What do you think can be done to further improve the cost performance of such building changes?
Further improve the cost performance. I don't know if government can include those tenement buildings into the current grants, but I consider this unlikely to happen considering this current financial problems. Now, obviously, if the costs of fuel, electricity, and the gas, then the performance will be much better.
Okay. Well, we are waiting for more questions. Question from me. Could this system completely replace radiators, do you think?
Oh, actually, I think it can be. And in some new buildings, actually, we use for example, ground heating and wall heating. So therefore, we can have a complete free obstructions in an interior space. So therefore, make interior design and the furnish arrangement much flexible, and so it is possible. And also because you use lower temperature and a large surface area, so therefore in terms of heating quality is much better than those created by radiators.
Again, one question from me. What building types would be most suitable for this system?
Types of buildings?
Yes.
I actually have this, in a very early stage of this project. Actually, I'm considering nursing home as the ideal place. For example, it's occupied all the times. And so therefore, you have one side to be heated during the daytime and bedroom during the nighttime. And also low surface temperatures is the recommendation for those heating systems in nursing homes, because that minimize the chances of burning for older people. So nursing homes and nurseries, schools, schools probably not good because they just occupied in the daytime.
Okay. Do we have any more questions here? We don't have any questions from the online audience. Well, if we don't have any questions, we can close this seminar today. I would like, first of all, to thank Wang for an excellent presentation and interesting answers, and to thank our viewers online and here at the seminar room for their questions. And I would like now to advise everyone that the next submission deadline for our applications for feasibility studies and academic consultancy is 13th of May, so in a week's time. If you have any questions regarding the applications, please do contact me. I will answer your questions. We still have 34 awards for feasibility studies to give and 11 for academic consultancies. We look forward to receiving your applications and to your feasibility studies that can also be then presented through our seminars and webinars. Our next seminar and webinar will be on assessment and application of zero carbon building in Scotland. The speakers will be Professor Prof of Heriot University and David McEwen of IES Ltd. This seminar and webinar will take place on 27th of May 2011. I would also like to remind you that we invite sponsorship of our seminars and webinars, and if you would like to learn more about sponsorship opportunities, please do contact us. We look forward to meeting you again at our seminar and webinar on 27th of May. Thank you very much for watching here and online. Thank you.